MBA633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this clip, we will work a problem to see how one goes about doing hypothesis testing involving two population variances. So we have a manufacturing context here, and we have a drill that punches holes through sheet metal, and the holes are supposed to be 0.5000 centimeters in diameter. Now, before and after a new press is installed, the hole diameter is carefully measured for 12 randomly chosen parts. So the raw data is given over here. So for the 12 parts with the new press, the hole diameters are given here, and for the old machine, so the first column is with the new press, and the second column is the 12 part measurements for the old press. And we want to check at 5% significance, does this evidence prove that the new drill has lower variance? So the two populations that we are looking at is the holes made by the old machine, that's one population. The other population is holes made by the new machine, and we got our raw data here. So the two population parameters that we are comparing is sigma L squared and sigma n squared, L and n referring to old and new machine respectively. So remember, our guideline for setting up hypotheses, we want to set them up in such a way that whatever claim it is that we are trying to establish should be the consequence of rejection of the null. Therefore, my alternate hypothesis would be sigma squared L, the variance with the old machine, is greater than the variance with the new machine, sigma squared n. So I have the two population parameters, the two population variances, sigma squared with the old and the new, and sigma squared L greater than sigma squared n, because setting up this way would imply that if we do go with this claim, it's the result of rejection of the null. That leaves us with the null being sigma squared of the old machine, L, is less than or equal to sigma squared n. Okay, so another way of saying the same thing is that sigma L squared divided by sigma squared n is greater than 1, and the null hypothesis, another way of stating this, is sigma squared L divided by sigma squared n is less than or equal to 1. Okay, and again, if you recall, all hypothesis testing starts with the assumption that the null is true as an equality. And we discussed in class that if sigma 1 squared is equal to sigma 2 squared, so if the null is true as an equality and the two population variances are in fact equal, then we know that this statistic S1 squared divided by S2 squared, where S1 and S2 are the two sample variances, the ratio of S1 squared divided by S2 squared has the F distribution, which looks similar to the chi-square distribution in that it is not symmetric, it's non-zero, it doesn't extend to negative values of F, and it's sort of skewed to the right, and it has degrees of freedom associated with it too. So to check our hypotheses, what is the statistic that we're going to look at? We're going to look at the F ratio, which is simply SL squared divided by SN squared. Notice that we have deliberately structured the ratio in such a way that the higher variance is in the numerator. So the F ratio that we would get from the sample statistic would be always greater than 1. So be careful to set up your F ratio in such a way that the sample variance that's higher is in the numerator. Okay, so the two sample variances have already been computed for you over here, and you can see that the sample variance for the old machine is higher than the sample variance for the new machine, and that's why we've set up the ratio in this manner. So with the data that we have, this is equal to, let's see what we get, equal to SL squared divided by SN squared. It's 9.65. I sort of shifted one cell below, but that's what the F ratio is. So Here we are on the x-axis is 9.65. So next step, we will use this ratio to decide whether or not to reject the null. How do we go about doing that? You know, one of the ways to do so is to use what is called the p-value method. And when one is using the p-value method, essentially what you're computing is the, in this case would be the yellow shaded area. So the question one asks oneself when computing the p-value is, how likely is it to obtain a test statistic that is at least as extreme as the one I saw, provided the null is true as an equality. Now this entire ratio 9.65, this value that we got of the f, is based on the assumption that the null is true as an equality. So the question we are asking here is, what is the probability of f being greater than 9.65? What is the probability of getting a test statistic that is at least as extreme as the value that you just got, namely 9.65, provided the null is true as an equality? So in order to do that, I would have to use the f distribution in Excel. So let's see what that gives us. If I can get my cursor over here, is equal to f dist, and it asks what's your position on the x-axis. Is 9.65, and followed by degrees of freedom of the numerator and degrees of freedom of the denominator. The degrees of freedom of the numerator is sample size of the numerator minus 1, which is 12 minus 1, 11. And what's the degrees of freedom for the denominator? It's equal to the sample size for the denominator minus 1, which is also 11. Okay, so here we go. The value that we get is 0.000372. Physical interpretation of this very small number is that if the null were true as an equality, the probability of getting a test statistic at least as extreme as the one we got, namely 9.65, is 0.03%. Okay, now our alpha is 5%. So I'm willing to accept a 5% chance of making a type 1 error. And what my data is telling me is that if the null were true as an equality, then the likelihood of getting such an extreme f statistic or something higher is only 0.03%. They're certainly much lower than our p-value, so rather than our alpha. So the situation we have here is that the p-value is less than alpha. In fact, it is much less than alpha. So I end up rejecting the null, because it is highly unlikely that we would see such an extreme test statistic if the null were true as an equality. We say, well, our assumption that we started off with must be false, so we reject the null. The entire analysis started off with the assumption that the null is true as an equality, and we are finding that under those conditions it's highly unlikely that I would get 9.65 purely by chance. There's always a very small chance that it did occur randomly, but that chance is 0.03%, certainly lower than the chance I'm willing to accept, which is 5%. So I say I'm comfortably say I reject the null, meaning I would end up saying that yes, at the 5% level of significance, I will conclude that the variability of the drill holes with the new machine is lower than the variability of the drill holes, variability of the diameter of the drill of the holes for the old machine. That would be my conclusion at the 5% level of significance. In fact, even if you use a 1% level of significance, since the p-value is even less than 1%, even at a 1% level of significance, I would be comfortable rejecting the null. Now, if you wanted to use the critical value method, you would find an f critical first of all, which means what value of f on the x-axis do I need would I call it very extreme? So when would I call the f value very extreme? So here I would need to use the inverse function over here. I would use equal to f(inv), and it says what probability do you want? Like the chi-squared, the f inverse needs the area to the right. So I'm willing to accept a 5% chance of making a type 1 error. So the area to the right would be 5%. The degrees of freedom would be 11 for the numerator and 11 for the denominator. In both cases, sample size -1. So I end up with 2.81. What does that mean? It means that if I'm willing to accept a 5% chance of making a type 1 error, then any f statistic that is higher than 2.81, I would consider that extreme enough not to have happened purely by chance. And my sample is telling me that the f value is 9.65. That's what I got from the sample. That's way more than 2.81. So the situation I have here is f is greater than f critical. So I consider anything more than 2.81 extreme enough, and what I found from the sample is 9.65. It's certainly comfortably above 2.81. So I come up with the same conclusion: reject the null. So whether I use the p-value method or the critical value method, I end up with the same conclusion, namely that the variance of the drill holes with the new press is smaller than the variance of the drill holes with the old press.